All right, so here we are again talking about the next question, question number 3 of our P17, where we have our Atwood machine. It's actually a half Atwood machine, where we're looking at as the mass falls and a cart is dragged across it. We're trying to find the final speed, the acceleration, and the tension. Okay, I'll go through all the steps here. We kind of already see a few of the answers popping up from my previous work, but the process is going to be the same. We're going to take all the original conditions and all the final conditions and plug them in here. Okay, so let's try to pull everything together as neatly as we can here. So we have M1 was 0.5 kilograms, M2 was 0.025 kilograms. Okay, and then what else did we know? H1 and H1 prime did not change. So I can call that 0 meters. Okay, you could have said 0.85 and 0.85, but the fact is that it's not going to change. So there's going to be no change in potential, which is going to be an advantage for us. Okay, and then H2 goes from 0.85 meters down to 0 meters. Okay, and then V1, V2 initial starts at 0. Okay, and then V1 prime. Okay, this is tied together on a string, so that is going to equal V2 prime, and that is what we're looking for. Okay, so that's the goal. Okay. All right, so if we have those conditions, then we can start going through this. So again, it saves you a lot of work if you can identify anything multiplied by 0. So we know this is what we're looking for. These are not zeros, okay? But this starts off and ends at the same height. So we know at least, very least, there's no change in potential energy. We can call those 0. Okay. We know everything starts off at rest. So those are all 0. Okay. So we said these are not 0. This one ends on the ground. So this one is 0. Okay. So now we can simplify this. Okay, so now we can go through that, and so we're going to have M2 GH2 equals. Okay, and those two are going to be identical. Okay, so that'll be a lot easier once we get our numbers in, but this is a great place for us to plug in the numbers now. Okay, so we can now do this, and we can say 0.025 Okay, remember this is what we're looking for. Okay, and we said these two are identical, so I'm just going to set this equal to V. That's the number we're looking for. All right, so we're going to plug this in here. What we get down here is 0.20825 joules, 1/2 of 0.5, 1/2 of that. Okay, we can now combine like terms and divide both sides, and we should get Okay, so that is going to be part A. All right, now number 3, part B, you see I already have the answer written out over there, but how did we get that? Okay, well, we know the initial velocity, right? We know V0 was 0. We know V1 is this one right here. And we knew that the distance was 0.85 meters. What we don't know is time. So we need to find a kinematic equation that does not use time, does use this, okay? So we can just use this one. Okay, what are we looking for? We're looking for acceleration. And this is, okay, so now we can just isolate this and we should get our acceleration equals 0.4. Okay, so that should take us through to part B. Okay, so hopefully you see why I wrote this number down, because now we need to use this number to find the tension on the string. Okay, and there's actually a few different ways we can solve this, right? I'm going to jump right to the easiest way. Okay, if we look at M1 and look at the F, okay. All right, well, we have mass and we're looking for force. What does Newton say we can do? We can do, okay, so we can just do the mass 0.5 kilograms times 0.47. Okay, and that gets us the number we're looking for here. Okay, so that's 0.24 newtons. Okay. So while we're here, we can also look at other ways to solve this. We could have also looked at that M2, okay? Remember that was equal to 0.025 kilograms, okay? And then we had tension here and the force of gravity there, okay? So this is going to equal mass times gravity. Okay, because now our sum of our forces and the y would also equal mass times acceleration. Okay, so now we could do force of gravity plus tension, what they're going to be opposite signs, equals 0.2025 kilograms times my acceleration, which we still have from before. Okay, so if we plug this in here, okay, we get that 0.025 times 9.8 plus tension is going to equal 0.025 times 0.47. Okay, notice this does not have mass in it, so we cannot divide all the way through by mass, but what we get is number fairly close to this again of about 0.24. Okay. Okay. Heck, why don't we try to do this one more? We could actually do this 2 more ways. Okay, we could also do work equals force times distance. If we looked at this number, okay, 0.20825 joules, that's how much work they had to do to lift this mass. In order to go from here to here, that's how much work was done to lift the mass. So that's a joule is a joule is a joule. So that means we can now use that number to find our force times 0.85 meters, And guess what? Your force comes off pretty close to 0.24 newtons again. Okay. If you really wanted to be complicated, there's one other way you can do this, and that is with our masses here. Okay, we can do force of gravity, tension, tension, and we can do the sum of our forces, the y equals ma, sum of the forces. This was, we had 1 here and 2 there. Okay, sum of the forces here is going to equal m1 times a. Those are going to be both a's. Okay, and then we would have to do simultaneous equations to solve for one and then the other. Okay, that's possible, but that's a lot of work. We don't need to do that. We found the answer. We can be done.